So we have another problem on integer programming, which is fixed cost production planning, and it's actually a mixed integer type of problem. So just to give you a little bit of background, we already covered this example in class, but just to give you another example, let's say, as an example, just to explain this type of problem, let's say we have a club, and so this is a club, but then if you want to become a member of this club, you have to pay one registration fee, and then there is another type of fee which is the usage fee. So the registration fee, it's a non-refundable fund, and it's actually a fixed cost. Doesn't matter whether you use it or not, so you have to pay it upfront. And then usage fee is variable depending on the amount of product or service that you receive from that club. It can change from month to month, for example. So we did a few examples in this course. So sometimes we don't have any fixed costs, but we do have variable costs. So if you remember the production planning example that we did in chapter 11, that was an example of this. So depending on the amount of production, we had to pay a variable cost, but there was not any fixed cost in that problem. And another example that we did in chapter 12 was capital budgeting. In chapter 12. And in that example, we had fixed costs, but we didn't have any variable costs. So if you remember, like buying an apartment or buying a house, that we have to pay a price, right away, immediately, and then there was no variable cost after that. Or let's say capital budgeting, when we have like different phases of product development, for example, we have fixed costs, and after you incur those type of costs, there's no variable cost after that. So for the first example, when we have variable costs and we don't have any fixed costs, we can solve those using LP, linear programming. And then when we have only fixed costs without any variable costs, we can solve it using binary LP, BLP, binary linear programming. And in this example, when we have production planning with fixed costs, that's again chapter 12. So when we have both of them, it's actually a case of mixed integer programming. Mixed integer linear programming, which is the case that we just want to solve it right now. Another example of these can be, so if you imagine Target, if we compare Target versus Costco. So at Target or Walmart, for example, let's say if you can buy the whole purchase of a year, for example, at one shot. So if you go to Target, you don't have to pay any fixed costs. You can simply go ahead and make your purchase, and at the end you pay, depending on how much you purchase, you pay a variable cost. So in here, so the cost is variable, And your decision, if you go to target, your decision is how much to buy. So let's show it with xi, for example, and I is the type of product I, x is the amount that you want to buy, and the only thing here is that it's going to be a continuous decision variable, and it just cannot take negative number. That's it. But it can take any other number. But if you go to Costco, for example, there's two sorts of costs that you have to pay. There is a fixed and variable cost. So the fixed cost is the membership cost. So, and then the variable cost depends on how much product you buy from them. The fixed cost, it's so you have to make two decisions here. If you want to go with Costco, the first decision is whether you want to be a member or not. And then if you become a member, then how much to buy. Again, if I show xi as the amount of product that you buy, there is another variable before xi can take positive numbers. Let's just show it with yi. And then this would be a 0, 1. So you can be either a member or not. And then as soon as yi gets 1, becomes 1, xi can be any positive number. And if you don't become a member, if it's 0, then xi would be equal to 0. You cannot purchase from it. So in those cases, when you have a fixed and variable cost, so there are two types of decisions to make. First, whether you want to become a member, whether you want to so in production planning, whether you want to establish a warehouse, and then how much you want to produce. So in the case of Costco, whether you want to be a member or not, how much do you want to purchase? In the case of production planning, whether you want to establish a plant, whether you want to build a warehouse, and then second, build or not, how much to produce, and then these two decisions they have to be connected. So before you build, you won't be able to produce. So if you don't build, the amount of production would be 0. So you have to make sure that these two are connected. And I mean, let me go back again here. So xi and yi, the way we connect these two is that for example, xi can be less than 100 units. So we have a capacity limit for production if we become a member, for example, or if we build our plant. So we have a capacity limit. This 1,000 is the maximum amount that we can purchase from Costco, or the maximum number of products that we can produce from in our plant. But then this relationship, this inequality would hold if yi is equal to 1, if we become a member or if we build our company or plant. So if we just add yi here, so if yi is equal to 0, xi, assuming xi would be a non-negative number, xi, if this is 0, xi less than or equal to 0, xi can be only 0. And if yi is y, xi can take any number from 0 to 1,000. So this constraint actually takes care of the relationship between a binary decision and a continuous decision. Whether or not to become a member, this one, how much to purchase, how much service to get, whether or not to build the plant, how much to produce after building. So that's a little bit of background, but let's go to our question and try to formulate it and try to bring it to Excel. So like I said, it's always very important to read the question very carefully and understand every single part of it. So there are four products that can be produced, and then each product needs manufacturing operations in three departments: department A, B, and C. And we have the labor hour requirements for each product within each department. And then we have some limited resource in each department. So 500 hours, labor hours in department A, 350 in department B, etc. And then 440 in C. And then we have profit contributions per unit for each product. And we have the setup cost. Now that we have setup cost, it means that it's a setup cost, it's a fixed cost. So depending on whether you start to produce or not, you have to pay this cost. There are two operational and market considerations. First of all, the product 1 and 2 are mutually exclusive. They cannot be produced together. And then second, the maximum demand or maximum capacity for each product is 1,000 units. So this we will use it when we want to connect XI's and YI. So we want to formulate a binary integer linear programming to maximize total profit, and then we want to solve it through Excel. So let's get us started. So let me just go here. So we have four products. So like I said, this is a fixed cost production planning. So we have two decisions to make. So we have four products. The first question is whether, so let me just write it this way. Decision variables. Whether or not to produce product I. And let's show it with y I, where I can be 1, 2, 3, and 4, sorry. And yi can be 0 or 1. 1 means yes. 0 means no. Yes means that we want to produce product I. And 0 means that no, we don't want to produce it. The second decision that we have to make is how much. How much to produce. How much to produce from product I. And let's show it with xi, and xi can be any non-negative number, and I is 1, So the objective function that we want to maximize here so if we go back to the question actually, in order to maximize the total profit, that's our objective function. So we want a production plan, so these are the decisions, and then this is our objective, maximum total profit. So we want to maximize total profit maximum profit, and it's equal to so profit margin of each product. So if we go back to the question, so the profit margins are 25, 28, 30, and 20 for each product. 25 for product 1, so let me just write it this way, 25. So if we produce if we produce 1 unit from product 1, we get $25 profit. But if we produce X1 unit, we get 25 times X1 unit of dollar actually profit. And then I'm not gonna write it, so it's the same. So it's going to be 25 x1 plus 28 here, 28 x2 plus 30 x3, etc. Let me just write down one more. 28 x2 plus 30 x3 plus x3 and 20 for x4. And then there is a setup cost. So this is our variable profit minus setup cost. And then setup cost is 400, 550, 400 for product 1. So we incur this cost if y1 is equal to 1. If it's 0, it's going to go away. It's not going to be a part of our profit. But if it's not going to be a part of our cost. But if this takes 1, we have to incur a $400 cost plus 550 y2 plus 600 y3 plus 300 y4. So this is our objective function, and then we have a few constraints to satisfy. Constraints. So the first constraints that I'd like to write here is so we said so we have to, there's 3 things that actually we have to take care of. The first thing is that product 1 and 2 are mutually exclusive. So this means that out of x1 and x2 we can only produce one of them maximum. Either one of them or neither of them basically. So product 1 and 2 mutually exclusive. So y1 is whether we want to produce 1 or not, and then y2 is whether we want to produce 2 or not. So if we produce them, they're gonna take if we produce product 1, y1 is gonna take 1. If we produce 2, product 2, y2 is gonna take 1. So there's only one case where both of them actually can be, we don't want both of them to be produced together. So if if the sum of this can be anything except 2, this sum, we don't want this sum to take 2. So it can take 0 and it can take 1, but not 2. If it wants to take 2, it means that they both are being produced, and this is not something that we want. So if we just make it less than or equal to 1, we're actually taking care of this situation. So this is a mutually exclusive that you should already know how to write. So the next thing that we have to define here is that we have a limited resources. We have limited resources for labor hours in different departments. Yeah. So the total labor hour that is used from department A should be less than 500, less than or equal to 500. So how do we write it? So for each product, for each unit of product 1 that is produced, we need 1.5 hours, labor hours from department 1. So let me just write it this way. So resource, limited resource or labor hour resource requirements. So for department A, if we produce 1 unit of product 1, we need 1.5 hours from this. So it's going to be 1.5 x1. This is the total amount of labor hour from department A that production of product 1 needs, plus 2.8 x2 plus 2 and 1.6, 2 x3 plus 1.6 x4. This is the total hours of labor that is required, that is needed from department A, and then this cannot be greater than 500. So this has to be less than or equal to 500, which is here. Where is it? 500. The labor hours available, 500 in department A. 3. Let's just quickly write the other two. So that's actually going to take care of our labor hour limitation. So this was for department A, this is for B, and then this is for C, department B, department C. So, and then the most important set of constraints is when we connect xi's with yi. So we haven't done that one yet. So like I said, continuous variable xi should be less than or equal to the maximum capacity, maximum production capacity, or maximum demand, whichever we have available, which in here is maximum demand. So let me just write it this 1000 is our maximum demand, maximum demand, and this would hold only if yi is equal to 1. So we have to have this set of constraints: xi less than or equal to 1000 times yi. And if yi is, so this linear equation would tell us that if yi is 0, then xi can only be 0. If yi are 1, xi, and we already know that xi are non-negative numbers. So, and then there is no point. The model, since we have a negative coefficient for the cost, so if xi is 0, the model will not make yi equal to 1, because otherwise we have to pay a setup cost. So the model will take care of if xi is 0, we have actually the option here. Xi can be 0 and yi can be 1, right, in here. But then it's not gonna happen, because if xi is 0, yi can also be 0, like here. And since we have a negative in a maximization problem, the problem is going to take care of it for sure, and it's going to make it equal to 0. So, and then last thing is that we already defined it, but these are binary, yi 1 to 4, and xi's are non-negative, again I 1 to 4. So now let's go to Excel and try to solve this. So let me just copy this table from Word to Excel. Let me just copy and then we had, for each product, we had profit margins, and we had setup costs, and we had a maximum demand for each one. So profit margins were 25, 28, 25, 28, 30, and I think 20. For product 2, setup costs 455. 455 and 600 and 300. And the maximum demand for each one is 1000. Fixed. So, and then we have, for each department, we have available hours, 500. 500, 350, and 40. Yes. So we have all the parameters from the question here in our Excel. Next thing is to assign empty cell for decision variable. So we want to know, so we have 4 products here, whether to produce, whether or not to produce, how much so we have 8 decisions to make. And then objective function, is, if we go back here, you'll see that objective function is the sum product of xi's and profit margin minus sum product of setup cost and yi. So let me show you the formula that I use. It's going to be equal sum product of how much to produce xi, comma, profit margin minus another sum product of whether or not to produce, comma, the setup cost. So now let's go ahead and write down the constraints. So the first constraint, as we had here, mutually exclusive constraint. So let's write it this way. So left hand side is the sum of whether or not to produce product 1 and whether or not to produce product 2, y1 and y2. So let me just highlight this one, and then we know that this should be less than or equal to 1, as we had here, this one, y1 plus y2 should be less than or equal to 1, and then we have labor hour resource limitation, resource constraint. So we had 3 departments. Let me just put it here. So if we go back again here, we'll see that these are some products of xi and working hours from each department. So if I go back here, it's going to be for department A, it's going to be some product of the working hour per unit from department A, comma, the amount of production of different products. So this should be less than or equal to 500. And then in order to be able to copy this formula, I'm gonna fix my decision variables, and then if I drag it down and drag everything down, actually it's gonna be all right. Let's see. For department C is how much some product of how much we produce and working hour from department C. So this is good. And then last thing would be the basically the connection of these two sets, whether to produce and how much to produce. And we need that last piece of information here. Maximum demand for each product is 1,000. So we need that one in here. So did I write it here? Yeah. So xi should be less than or equal to 1,000 times yi. So I'm gonna write it this way. So again, we have 4 products. And then the amount of production for each product. I can call this connection constraints, or fixed cost constraints. Fixed cost constraints. Department mutually exclusive product 1 and 2. So let's write that formula. So these guys should be less than or equal to xi should be less than or equal to 1,000 for product 1. This is the maximum times whether or not to produce product 1. And then let me just right, and then so we want for product 1 x1 the amount of production for product 1 to be less than or equal to 1,000, given y1 is equal to 1. So 1,000 times y1. So now we have everything ready. We just need to go to solver and solve this problem. So if we go to solver, so the objective, so we want to maximize the profit by changing these 8 cells, and then subject to the following constraints. We want this to be less than or equal to 1. Then we have department working hour constraints. So we want the total hour needed to be less than or equal to the total hour available for all of the departments. And then we have a fixed cost constraint where actually we connect these binary decisions with the continuous decisions. So we want these 4 guys to be less than or equal to these 4 guys, and it's going to take care of them one by one. So add, and we have one more constraint to add. We shouldn't forget that whether to produce or not. It's a binary type of decision. It's a 0-1 type of decision, and we have a simplex LP to solve it, and nothing actually in here is negative, so we can check this one. So everything is ready. Let's just go ahead and solve it. So at the end we produce product 1 and product 4. This looks to be good actually. If you check out of product 1 and 2, only product 1 is produced, and then we're using everything that we have available from product, like the work hours available from department A and C. So we're using them, so these are binding constraints, but then we have still resources available from department B, and so we're not reaching out to the maximum demand because of our constraint here. Because of these two constraints, we won't be able to satisfy the maximum demand available. But then that's okay. That's what it is. So we actually are producing product 1 by 82 units, product 2 by 235 units. And if they cannot take integer numbers, if they cannot take continuous numbers, since these are very big numbers relatively speaking, so we can round them, and this can be 82, this can be or 83, this can be 235 or 236. That's it.